Right. Inside this container, let's say there is some object fully immersed. Assume its volume is V. If the container is accelerated horizontally, okay, let's say the horizontal acceleration is A, density of liquid is rho. Fine. Find out the net buoyant force, okay, acting on this object. So how is this different from the cases we discussed before? Buoyant force arises due to pressure variation. Okay, it's basically force due to the pressure distribution around the object. Now, had the container not accelerated horizontally, okay, had this acceleration not been there, the pressure gradient would have been in the vertical direction. Okay, pressure will increase as you go down. So basically, what happens? Forces from above will be weaker than forces from below. In that case, buoyant force will be in the upward direction. You know how to derive it. Now, if the container has a horizontal acceleration, what happens is there will be a pressure gradient in the horizontal direction as well. Okay, there will be pressure variation in the horizontal direction. As a result, the forces from the right side, will be weaker than forces from the left side. It will experience a buoyant force to the right. Okay? So derive an expression for the total buoyant force acting on this object. Try. See, understand how to derive buoyant force in any case. Now, when the container starts accelerating, the liquid surface, the free surface of the liquid will not be horizontal anymore. It will be tilted, and we have seen situations like that. Okay, so let's assume that is what happens. Right, and assume this object is present in this container. Okay. Now, whether the object stays there itself or sinks, moves to the right, moves to the left, all that will be determined by the buoyant force acting on it. Okay. Now, how to derive the buoyant force acting on this object? Visualize the boundary first. Okay. The volume occupied by the object. Now, forget the object for a while. Instead of the object, let's say the liquid itself was present in that space. Okay. See, if the liquid itself is present in that space, no, it will be in equilibrium relative to the container. It will be in equilibrium with respect to container. Okay, now the container is accelerated to the right. Think of the forces acting on that part of the liquid. One obvious force acting is its weight. Weight acts through the center of gravity of that liquid. Density of liquid into volume into G. Okay. Now, with respect to container, it will be in equilibrium. Now, container is an accelerated frame of reference. And when observing something from an accelerated frame of reference, you should assume a pseudo force to be acting on it. You know how to apply pseudo force. Mass of the object multiplied with acceleration of the frame of reference. Now we have put the object aside. In that boundary, we are assuming the liquid itself is present. Okay, this will help us in calculating buoyant force. If the liquid is itself is present, it will be in equilibrium. That's the idea we are using. So buoyant force is mass of liquid multiplied with acceleration of frame rho VA. Sorry, not buoyant force. Pseudo force is mass of liquid rho V multiplied with acceleration of the frame A. So with respect to container, these are the forces that act on the liquid other than buoyant force. Okay. Now this part of the liquid has to be in equilibrium. So we can conclude that buoyant force in this case should be balancing these two forces. Therefore, buoyant force acts in this direction. Okay. Basically, pressure gradient will be perpendicular to the free surface. You know that. So the forces acting on the free surface of the liquid will be like this. They will increase as you move in the direction of pressure gradient. Okay. The resultant of all these small green vectors that I have drawn is the buoyant force that we have indicated. Buoyant force here, therefore, will be rho Vg j cap plus rho Va I cap. Or if you only want the magnitude, it will be rho V under root A square plus G square in this direction. Okay. Now, if that space is filled with some other material, irrespective of what material it is filled with, the pressure distribution is going to be the same. If the pressure distribution is the same, the resulting buoyant force will be the same. So how much is the buoyant force acting if some other object is present there? The buoyant force acting will be the same. Pseudo force will change, weight will change. Okay, buoyant force arises due to pressure distribution of the surrounding liquid. No, so this same amount of buoyant force will keep acting. These two forces will change. Okay, and depending on which of those two forces are stronger than buoyant force, the object may sink, it may rise, it may move to the left, it may move to the right. Vanilla, is this clear?
Yes, sir.
Okay. So in any case, if you want to find out how much buoyant force acts on an object, imagine liquid itself in place of the object. To keep that liquid in equilibrium, whatever force is necessary, that itself is buoyant force. And that liquid has to be in equilibrium with respect to what? With respect to the container in which it is present. Okay. So based on this, try to answer this question. Suppose there is a spherical balloon. Okay, I can do the coloring later. Let's say there is a spherical balloon which is tied to the bottom of a container like this. Okay, balloon is filled with air. It naturally has a tendency to rise because you know air is less dense than water. It'll have a tendency to rise up, but it is tied to the bottom of the container with a string like this, right? If this container, like if the container is kept stationary, the balloon stays in this position. Fine. But the question is, if the container is accelerated horizontally to the right, which way does the string tilt? Will it tilt to the right, tilt to the left, or will it stay in that vertical position itself? Okay, that is the question. Try. Had the container not accelerated, the balloon would have had a tendency to move in the upward direction. Okay, had it not been tied with the string, it would have risen up. What does that mean? That means the buoyant force acting on the balloon. Okay, let's consider a non-accelerated container first. If it's non-accelerated, the buoyant force acting on the balloon would have dominated its weight. Okay, balloon's weight is very less. Buoyant force will dominate. That's why it has a tendency to rise up. Now, if the container is accelerated and it is accelerated to the right, what will happen is there will be a pressure gradient developed to the left. Pressure increase as you move to the left. Okay. Due to that, what will happen? There will be some buoyant force acting this way also. Okay, like what we discussed in the previous case here. If container is accelerated horizontally, this is the overall buoyant force. Means it has a vertical component and a horizontal component. Vertical component of buoyant force arises due to pressure variation, which happens due to gravity. Okay. This is buoyant force in the vertical direction. Horizontal component of buoyant force arises due to pressure variation horizontally. And what gives rise to horizontal pressure variation? This acceleration gives rise to horizontal pressure variation. So buoyant force will have a horizontal component as well. Okay. So here also there will be a horizontal buoyant force component developed when the liquid accelerates to the right or the container accelerates to the right. Now see, the question is asking you to find out which way the string tilts. Now, which way the string tilts depends on which way the balloon moves with respect to container. Because here the container is accelerating, the bottom of the string will also move, not just the balloon. Both bottom and balloon will move. Finally, which way the string tilts depends on how the balloon moves relative to the container. Okay, or relative to the bottommost point where it is tied. That is point of the container only. Okay, that is a point which belongs to the container. So you have to look at the balloon's motion with respect to container, and container is a non-inertial frame here. So you will need to apply pseudo force. Okay. Now, depending on which force dominates out of the horizontal buoyant force component and the pseudo force acting to the left, out of these two, whichever force dominates, the balloon will or the string will tilt in that direction. Okay. Uh, Vanilla, tell me what is the expression for horizontal buoyant force? Assume volume of the balloon is V. Density of balloon will take rho naught. Density of liquid will take rho L. How do you write horizontal buoyant force?
The rho naught into V into
Hmm. Okay, let's clarify the idea. You said rho naught. Does buoyant force ever depend on the object that is placed in the liquid? చుట్టూ ఉన్న లిక్విడ్ మీద డిపెండ్ అవుతుందా ఆబ్జెక్ట్ మీద డిపెండ్ అవుతుందా
on the liquid, sir.
buoyant force depends on the liquid that is or the fluid that is surrounding the object, so it will never be depending on rho naught. Density of object depends on rho L. Okay, and horizontal buoyant force arises due to horizontal acceleration, so it will be rho L into volume immersed into A. Okay, that's what we proved in the last problem. The horizontal component of buoyant force is rho VA, where rho is the density of the liquid. Okay. Now tell me the expression for pseudo force. Basic expression: mass of the object multiplied with acceleration of frame. Rho naught into V is the mass of the object, balloon. Acceleration of the frame is A. Now think carefully and tell me out of these two, see it's a balloon. Okay. It has a tendency to rise up or float in the liquid. Tell me which term will dominate. In a non-accelerated container, the balloon would have had a tendency to rise up. What does that mean? Vertical buoyant force, that is density of liquid into volume into G. That is vertical buoyant force, no? In non-accelerated container. This would have been greater than weight of the object, rho naught into V into G. Fine. Or you could have said directly also, since the balloon has a tendency to rise up in the liquid, density of balloon is less than density of liquid. Okay. And if density of balloon is less than density of liquid, that means horizontal buoyant force is greater than pseudo force that is acting horizontally. And if buoyant force is greater than pseudo force, which way will the string tilt? It will tilt to the right. Okay. It is an interesting case actually. If container moves to the right, liquid surface will become like this, obviously. And the balloon, relative to the container, the balloon will move to the right side and settle somewhere like this. We have to assume it is completely immersed because that's the case under which we derived these equations. So it will tilt by some angle like this and settle. Okay. At what angle will it settle? it settles perpendicular to the free surface. So that angle we have derived already, tan inverse A by G. Based on that, you can tell this angle also, by which the string tilts before the balloon comes into equilibrium. Okay. So because the balloon's density is less than the liquid's density, buoyant force will be stronger than pseudo force. So if the container is accelerated to the right side, this is what will happen finally when the liquid settles. Is this clear? Any doubt in this? Okay. Next, uh, you know that if the liquid is denser than the object will float. Okay. Suppose there are two liquids mixed, two liquids of different densities, one denser than the other. So like if you pour oil into water, what happens? Anyone? If you pour oil into water, what happens?
Sir, oil will float on water.
Oil will float on water. You'll be able to see them separately, right? They won't mix. Okay. And why does oil float on water? Because it is less dense than water. Okay. Material having lesser density will float. Fine. Now consider U-shaped tube like this. Questions based on U-shaped tubes are very, very common and very important also from the examination point of view. Just a moment. Okay. Consider a U-shaped tube like this. Suppose you start pouring in liquid into one of the arms. Let's say it is initially empty and you start pouring in liquid. What will happen? The liquid reaches the bottom on one side, and does it stay on that side itself or does it flow to the other side? From everyday experience, we can tell it will definitely flow to the other side. Okay, and on the other side, it will start rising also. Why? Because if the height of the liquid is not equal on both sides, okay, for example, consider something like this. Let's say in one arm it is filled till this level, in the other arm it's only filled till this level. Okay, then what will happen? The pressure at this point will be P naught plus rho g, height in the left arm. The pressure at this point will be P naught plus rho g, height in the right arm. If the heights are not equal, these pressures won't be equal. And if these pressures are not equal, this part of the liquid that is there between these 2 points cannot be in equilibrium. Left side pressure is more than right side pressure, it will move to the right side. Okay. Fluids naturally flow from high pressure to low pressure. So that adjustment will keep on happening till the pressures become equal. At the at a given horizontal level, having a continuous fluid, the pressures have to be equal. So what will happen? This level will come down a little bit, this will rise up a little bit, and they will settle such that the level of liquid is same on both sides. So finally, what you see, sorry, finally what you see will be like this. Okay. Let's solve problems based on this. Suppose it's the same liquid, okay, in both arms of the tube, U-shaped tube. So the height will be equal. Assume the liquid's density is rho. One of you tell me, if we accelerate this container to the right side, this U-shaped tube is accelerated to the right side, what will happen? Will the levels of liquid in both the arms still be equal?
No, sir.
Okay. In which arm will the liquid be higher, left or right? Like Vanilla, on what basis did you say that the levels will not be equal?
Sir, the pressure will vary horizontally.
Right.
That's why you.
Correct. Okay. Yeah. For the levels to be equal, the pressure at this point, PA, should be equal to pressure at this point, PB. Had the container not been accelerated, okay, that would have been the situation because pressure develops only due to gravity in that case. But here, due to acceleration, there will be a pressure variation to the pressure increase as you move to the left. Okay. So when the container is accelerated, pressure at A must be greater than pressure at B. So as a result, what will happen? The height of liquid column on the left side will be greater than the height of liquid column on the right side. This is what you will see. Okay. And you can even tell how much will be the height difference if you know how much is the horizontal distance. Like if you know X, you will be able to tell Y. How? Because you know this angle. Had it been a full container, the liquid level would have become like this. Even if it's not a full container, the angle will be the same. You can prove it also if you want, but I won't be doing it now. You just write pressure difference between A and B in terms of heights, in terms of horizontal distance. You will get the ratio Y by X. And you will see that tan theta, which is Y by X, is again equal to A by G. Vertical pressure variation is due to gravity. Horizontal pressure variation is due to that acceleration. Okay. Next. Suppose there is one liquid. Let's say this liquid's density is rho. It's a non-accelerated U-shaped tube. If there's a single liquid, this is how it will settle. Equal level on both sides, in both arms. Okay. So now what we are doing is, imagine we pour another liquid into one of the arms, and that other liquid's density is less than rho. Okay. If the liquid's density is less than rho, it will have a tendency to settle at the top. It won't sink into this liquid. Okay. So the blue liquid will remain at the bottom. Yellow liquid will settle above it. Fine. I want you all to visualize and tell me if we add a small amount of yellow liquid in the left arm, what will happen to the levels of blue liquid in the arms? Okay. Think carefully and answer. If we add some lighter liquid in one of the arms, what will happen to the existing levels? See, we are adding a lighter liquid in one of the arms, right? Imagine some of that lighter liquid floating here. Okay, we'll first discuss why there should be any disturbance or if there will be any disturbance to this system. So imagine the lighter liquid floating here. Now, it is lighter than the blue liquid, that's fine, but it will have some density, it will have some weight. So when you pour liquid in the left arm, basically what you will be doing is you will be increasing pressure at A because the total height in the left arm is greater than the total height in the right arm. Okay. And like definitely pressure at A will be more than pressure at B. If pressure at A is more than pressure at B, then liquid will start moving from A to B. So that blue liquid that is there will adjust itself. It will decrease in the left arm. Its level will increase in the right arm. Okay. So let me draw that situation. And till when will that adjustment keep happening? That adjustment will keep on happening till the pressures at A and B become equal. Okay. Because that is what is driving liquid from one side to the other side. So what effectively happens is liquid level on one side decreasing. As the level decreases on this side, it increases on the other side automatically. Okay, just a moment. And how much ever the level of blue liquid decreases on one side, by the same distance, it will increase on the other side. That is also important. Let's say the blue liquid's level falls till here on the left side. You can clearly see by what extent it has decreased on one side. by the same amount, it will have to increase on the other side, because we know ideal fluids are incompressible. Okay. Incompressible means what? Its density, their density cannot be changed. So their volume effectively cannot change. So whatever is the decrease in volume on one side, same will be the increase in volume on the other side. Okay. This term is very important. You have to talk in terms of volumes. Okay. Now on the left side, it has decreased by some level. Let's call it y. On the right side, it will have to increase by the same level y. So it will rise till here maybe. Now, as this adjustment happens, pressure at A will decrease and pressure at B will increase. And at some instant, at some heights, pressure at A becomes equal to pressure at B. Once that happens, the liquid settles. Okay, actually, in a real life situation, it will oscillate for some time and finally settle like this, but it settles when the pressures become equal. Okay, this is what will happen. Fine. Now, we added a lighter liquid on the in the left arm. The blue liquid is the denser liquid, yellow one is the lighter one. So let's say this is the situation finally. Let's assume, okay, this is a very important assumption. Let's assume the area of cross section of both arms is equal. If area of cross section is equal, only then this decrease in height will be equal to this increase in height. Otherwise, the heights won't decrease and increase by the same amount. Why? Because it's the volume that has to remain constant. On the right side, if it is very wide, then you will only see a small rise in volume there. I mean, small rise in height there. Volume has to remain the same. Okay. So it depends on the area of cross section. If they don't mention anything, you will assume the area of cross section is equal. Okay. If they particularly mention that area is in the ratio 1:2 or something like this, then you will have to adjust the heights accordingly. Okay. So if the areas of cross section of both the arms are equal, then this is what will happen. Suppose the liquid density, the blue liquid density is 2 rho, yellow liquid density is rho. Let's consider something like this. And how much height of yellow liquid are we pouring? Let's say we pour height of yellow liquid equal to, I'll show it in this diagram itself. Let's say this height is capital H. Okay. I want you to find out the final difference in heights. Okay. Or just find out why. How much will the blue liquid level decrease in one arm? Derive an expression for y. Okay. Try this, both of you. Yes. See, when will the fluid or liquid finally settle? When the pressure at both ends of that horizontal part becomes equal. Okay, let's assume those pressures are equal. If those pressures are equal, then automatically the pressures at x and y should become equal, because A to x, it's the same liquid, the blue one. B to y also, it's the blue liquid itself. Now pressure at A is equal to pressure at B. Pressure at x will be pressure at A minus rho g into some height. Okay, you can call this height as L or something. Then here the pressure will be PA minus rho GL. Then at Y also the pressure will be PB minus rho GL. PA is equal to PB, so PX will be equal to PY. The pressures there will be equal. Okay. At the same horizontal level, if it's the same fluid below, then the pressures will be equal. Okay. Now we need that distance Y. We know that this total height is H. The height of that yellow liquid is H. Therefore, the pressure at X, in terms of that height, capital H, if you write, pressure at X will be atmospheric pressure plus density of the yellow liquid into G into the depth in that yellow liquid. On the right side, pressure at Y, what should that be equal to? It should be equal to the pressure created by this much of the blue liquid. If the blue liquid on one side goes down by a height y, then other side will rise by a height y. So this total height is 2y. So pressure at y will be P naught plus its density. The density of the blue liquid is 2 rho. G, the depth there is 2y. That's all. Equate these two now. We know that pressure at x must be equal to pressure at y. P naught gets cancelled. Rho G also will get cancelled. You will get H is equal to 4y or y is equal to H by 4. Good. But remember, you can't solve such problems blindly. You should ensure that the area of cross section is same on both sides. Only then decrease in height on one side will be equal to increase in height on the other side. Okay. Now you know okay, there will definitely be some difference in heights. Now you got y as h by 4. If y is h by 4, 2y will be h by 2. This height is h by 2. Left side yellow liquid height is h. Okay. So the total height in both the arms is not equal. Okay. This is h by 2 and this side it is h. The total height of liquid in both the arms is not equal. Now one of you tell me, any of you tell me, can we make these heights equal by accelerating this U-shaped tube horizontally? Can the heights of liquids in both the arms be made equal by accelerating the U-tube horizontally? If yes, which way should we accelerate it? To the right or to the left?
To the left.
To the left, correct. Derive that acceleration. How much acceleration should this U-shaped tube be given to the left such that the level of liquid in both the arms becomes equal? Now see, for the level in both the arms to become equal, left side has to go down, right side has to rise up. Okay. As left side goes down, some of you may be worrying about this level becoming zero. Okay. There may not be any blue liquid left on that side at all. Don't consider that possibility. Okay. Assume there is enough blue liquid that it does not become zero on the left side. Fine. In that case only you find out the horizontal acceleration required. So derive the horizontal acceleration. Good that both of you gave the answer that it should be accelerated to the left. Derive the horizontal acceleration such that the total liquid level becomes equal in both arms. Now you know how much is y. Situation was like this. Okay, you know the densities also. Blue liquid density is 2 rho. Yellow liquid's density is rho. Try this, I'll give you 2 minutes. The first thing you need to do is imagine that happening. Okay. Imagine the situation where liquid in both the arms is of the same level. So left side we will have to bring it down. Right side we'll have to bring it up. Just a moment. So this h by 2 won't matter anymore. Okay. This is how we want it finally. Right. All that we know is that this height is h. The height of yellow liquid is h. And if the height of yellow liquid is h, then the height of blue liquid on the other side should also be h because total level has to be same on both sides. Okay. Now just write expression for pressure and then you'll get horizontal this thing. And I think you'll need to know the length, horizontal length. Maybe that is where some of you are stuck. Okay. Take the horizontal length as L or you take it as X for convenience. That's all. So pressure at A, if you express now, it will be P naught plus density of yellow liquid into G into H. In fact, you don't have to take pressure at A. You can take pressure at this point and pressure at this point. Call them as some, okay, C and D. Yeah, PC and PC, PD, fine. Pressure at D would be P naught plus density of blue liquid 2 rho G H. Okay. And these two will definitely not be equal. Container is accelerated horizontally, no? So horizontally at the same level, there will be pressure variation. This way, if you see pressure at D minus pressure at C becomes 2 rho GH minus rho GH, that is rho GH. But horizontally, if you write this way, the pressure difference between 2 points which are at the same horizontal level is rho A into horizontal distance between them. So equate this to rho A x. That's all. A becomes GH by x. If the container is given that much acceleration, the overall level will be equal in both the arms. Is this clear to both of you? Right. Now let's go back to this situation. Yeah, if it's just one liquid itself, but container is accelerated horizontally, you know there will be a difference in the arms, okay, in the level of liquid in the arms. The same thing will happen if you do rotation also. Instead of giving horizontal acceleration, rotate the liquid about one of the arms. Then also this is what will happen. Okay. Then you know the free surface would have been parabolic like this. You know how to write horizontal pressure variation. Based on that, you can tell the height difference also. Okay. You can tell height difference in terms of omega. So right now I'm not solving problems like that, but in the worksheet they'll be given practice problems. Okay. In the rotated fluid, we know how to write pressure variation in the horizontal direction. Based on that, you can tell what will be the height difference between the arms if the U-shaped tube is rotated. Right. Fine. So Archimedes principle, U-shaped tubes, buoyant force. This much is enough about Archimedes principle and these U-shaped tubes. Next class, we will start talking about uh, moving fluids. We'll talk about something called streamline flow, and we'll discuss something called equation of continuity. After that, we will discuss Bernoulli's equation and its derivation. Okay, derivation is also very, very important if you are preparing for advanced. So next class will be on Monday. Monday we will start streamline flow and Bernoulli's equation. Okay. Thank you. We'll continue on Monday.